Well, thank you, everyone, for coming back to finish off this introductory lecture today. So what I intend to do today is to finish the PowerPoint presentation that I've labelled as lecture number 1. And I will also give you a little bit of homework to do before we meet again next Tuesday. Looking back over what I told you yesterday, I think I rushed through a few of the things that I was telling you about. So I'm just going to briefly go over those things again. The first thing I wanted to go over was the use of SAM, the System Advisor Model, the software that's available from NREL, which we're going to use to look at wind turbine operation in practice and photovoltaic operation in practice. And the advantage of SAM, as I tried to point out yesterday, was that if you can find a weather file for your location, then it's very easy to use to do basic system modeling. I found I was able to download a weather file for Calgary, and you can see that file is highlighted here. It shows the latitude and the longitude of Calgary, and following on from that is information that has the symbols TMY, and TMY is a very common quantity in these sorts of simulations. It stands for typical meteorological year. So it's meant to be a representation of an average year, in this case, of solar radiation data, because it's necessary to do these analysis for something that's typical of, say, the 20-year lifetime of a project. And that's what a typical meteorological year is meant to indicate. So I tried to find some data for Novosibirsk and I failed. And so when we get on to looking at solar photovoltaics, I'm going to get your help to see if anyone in the audience is better at finding things on the internet than I am, to see if we can find a weather file for Novosibirsk, and we can do some calculations for Novosibirsk as well. So I'm going to show you again a calculation, this time for Calgary. I think we did somewhere in the US yesterday. So that's the first part of the resource assessment. The next part is to choose the module that you are going to use. And when we get on to using SAM for wind turbines, we'll see that SAM has an equivalent large amount of data for different types of wind turbines as well. There's a default setting in all these parts of the program, so I'm not going to go through that in any detail, but you can see at the bottom of the screen, I can't turn my laser pointer on because I'm not in PowerPoint. You can see that these are the specifications for that particular module. You have to choose an inverter as well, and we'll talk a lot about inverters as we go through this course, because that is the method or the electronics that transfer or transforms the direct current power out of the PV system into AC power, which is usually what we want. Then there's some information about system design. And I pointed out yesterday, particularly, we're interested in the tracking and the orientation choices that SAM gives us. And one of the things that we're going to be looking at, if I can bring it up a bit better, is that SAM gives us the option of tilting, of tracking the sun, or it also allows us to have a fixed tilt angle, and a tilt angle is the angle of the module in the north-south plane, and the azimuthal angle, which is the angle in the east-west plane. We can also do some corrections for shading because we're going to spend a lot of time when we look at PV to understand how shading can be extremely important. Then if there are losses in the system, and we'll talk a little bit about some of these losses, which are typically not included in the manufacturer's specifications for particular PV modules. And some of these losses, like module mismatch, only come about when you aggregate, when you connect PV modules together in a string or a system. Then there's issues about the limitations that a particular electricity grid may have on the power that you are providing to it. We're not going to be looking at that, but we will have a look at all the other aspects of system design. And then when we finish all that, we can simulate the performance. And you can see for Calgary, the capacity factor is about 15%. That's actually a very healthy number. That is typical of sunny climates in mid-latitudes. The one we did yesterday, I think it was for Phoenix, Arizona, that was a desert climate. So you would expect that to have a higher capacity factor. On the other hand, one of the big problems that you have with desert installation of PV is that it often is operating at very high ambient temperatures. And we're going to see when we look at photovoltaic technology that typically the efficiency of a PV system decreases with increasing temperature. And that's a major issue for system performance. So I won't say anything more about SAM until we get onto the wind turbine section of the course, because we're going to use the equivalent wind turbine module in SAM. And as I said, we'll use it for the PV course as well. So I'm going to stop sharing that screen and start sharing the PowerPoint presentation. I better get the PowerPoint presentation up. And can I see it here? I better stop sharing and start again. Here we go. Okay, so now you should be able to see the slide that I showed you yesterday, that I had on. Just that's better. I was getting a bit of funny view there. So I'll turn the laser pointer on. I talked very briefly about power purchase agreements, which apply pretty much the same way for a wind farm as they do for a solar farm. And I realized after the lecture that I probably rushed through this part of it. So I'll go back and just say a few words about that. A power purchase agreement is a very common feature of wind farm or solar farm operation, and also for the project planning. It's so important that it has its own abbreviation. PPA, we'll see again a couple of times through this course, stands for Power Purchase Agreement. And the way it works is that a wind or a solar farm is typically designed to have a 20-year lifetime. So if I'm considering installing a wind farm, then all the calculations that I will do on return on investment, maintenance, and all those sorts of issues, they would be based on assuming that the wind farm is going to last for about 20 years. That's a typical number. And what I would like to do as a wind farm or a solar farm investor, because we've seen from the cost of wind turbines that they're not cheap, I would like to be able to settle as much of the financing of that project before the project actually starts. So a power purchase agreement in principle is very attractive to wind farm owners and solar farm owners, because it allows them to do the project planning over that 20-year lifetime, say, of the project. So it means that when they go to a bank or another financial institution to borrow the money to build the wind farm or the solar farm, they can tell the bank, we've got a power purchase agreement for 20 years, and that is how we're going to fund the project, and here's all the spreadsheets and whatever that we've done to do those calculations. So as I said, it's a very simple idea, but it is very common in the wind and the solar farm business. So I think that was probably I felt the main thing that I didn't spend enough time on yesterday. If there's anything else that people would like me to review, I'm very happy to do that. So just put a message in the chat if there's anything like that. What I'll do now is skip forward because we actually finished at about this point here. I had these slides prepared just in case I couldn't get Sam to operate efficiently or effectively under Zoom. So I'll skip through that. And I come to this point here. This is, again, information from the US. And I'm not necessarily biased or in favor of the United States for a lot of reasons. But one of the things that you will find if you get involved with renewable energy is that they have a lot of very good information. So, for example, the information that I've already given to you on what typical wind turbines look like and what the cost of solar photovoltaic installations are, a lot of that information is actually determined by American agencies. If I go to Canada to find similar sort of information, I can't find it. I can find little bits of it for, say, particular institutions. But as far as I know, there's no countrywide assessment of the wind market in Canada. So when I teach this course in Canada, I use the American data that I've showed you as well. So this is the last part of the data that I want to talk about. And this shows typical LCOE, which is another abbreviation, which is also a very important one for any sort of electricity generation system. It stands for levelized cost of electricity. Sometimes it stands for lifetime cost of electricity. The distinction, as far as we're concerned, is not very great. So the lifetime cost of electricity is meant to estimate the cost of electricity generated by these technologies over the lifetime of the project. And you'll see that the list here, and there's a website where I got that information from. It was current as of, I think, only a few months ago. These are estimates, by the way, that are based on actual prices, but also taking into account trends into the future. So it's divided into what are called dispatchable technologies and non-dispatchable technologies. And the term dispatchable, non-dispatchable, again, is a common term in the electricity industry. What it means is that if you have a dispatchable method of generating electricity, then you can more or less produce any amount of power at any time during the lifetime of the project. Not always, because you can see even technologies like coal and nuclear, they don't have 100% capacity factor because sometimes a coal-fired power station breaks down. Sometimes a boiler has to shut down for maintenance or a turbine has to be shut down for maintenance. So they're not actually available all the time, but they're typically available more than the non-dispatchable technologies, which are usually the renewable technologies. And you can see capacity factors here for onshore wind, typically what we saw in the lecture yesterday. The solar capacity factors that I think are a little bit high. I think probably closer to 20% would be realistic here. You can work through all the other costs that you can see on this table here, but I want to focus on the one that I've highlighted in green because that shows the total system cost. And you can see that the non-dispatchable technologies wind and solar, and I'm talking mainly about onshore wind, are significantly the cheapest of the technology. Okay, this is the point that I was making yesterday. We're interested in renewable energy because it mitigates greenhouse gas and global warming effects, but on the other hand, it is also cheap. And in Western Europe, for example, wind power is now the cheapest form of electricity generation. And that's even for offshore wind in Europe. And you can see that for the US, the offshore wind costs are significantly greater than the onshore wind costs. So it's going to be quite a long time in the US and probably much longer in Canada before the substantial offshore wind resources are actually used. Okay, now I want to finish off the introductory lecture by talking about probably the most important issue with renewable energy, and that is the issue of intermittency. And this term intermittency is going to crop up, it's going to come up again and again, particularly when we talk about wind power and solar power. What you see in this graph here is data that I got for 10 days in 2011 in Alberta. There's nothing specifically interesting about those 10 days. The only reason I chose those 10 days is that the data was available. And what you see in blue at the top of the curve here, at the top of the graph here, is the total grid power that was provided in Alberta over those 10 days, something like 8,000 megawatts. And you will notice that there is predictable fluctuations in that load. And if you count up the number of peaks and troughs in that data, you will see that there's 10 of them, because this is showing the daily cycle of electricity requirements in Alberta. The lowest point typically occurs at about 2 o'clock in the morning. Each of the divisions into a day starts at midnight. So there's midnight there. So about 2 o'clock in the morning is the lowest power demand. That increases by about 15% in Alberta to I think it's around about midday or a little bit later. These daily variations are generally predictable. For example, this is probably Sunday because it has the lowest maximum load. Many electricity systems have a much bigger difference between the peak power required and the minimum power required. In Alberta, the ratio of those peaks is relatively high. And that's because we have a lot of industry in Alberta. We have a lot of particularly industry in northern Alberta, which is extracting bitumens from the oil sands deposits up in Alberta. And those extraction processes run 24 hours a day. So this is the load that the electricity system in Alberta had to provide for those 10 days, July of 2011. Down the bottom, you probably already looked at it, in green is the wind power that was produced over that same period. And I have to make it very clear to you that the blue curve has been scaled down by a factor of 10. Okay, the real numbers for the grid power are around about 8,000 megawatts, but I scaled them down by a factor of 10 so that I could fit them on the same graph as the wind power production. So in 2011, maximum wind power production over those 10 days was something like 600 megawatts compared to about 8,000 megawatts of total grid demand. In other words, the penetration, and this is another term that we're going to be seeing in this course, the penetration of renewable energy in Alberta at this time here was quite small. It was only about 6 or 8%. Now, the next thing to note from this data is that the wind power indeed is intermittent. Okay, the wind power is produced when the wind blows, not necessarily when you want it. So, for example, on day 2, we're getting a lot of wind power at the points where the maximum system demand is. But if we go over to day 3, we get the reverse. There's no strong correlation between the time of day and the wind power production. So the wind power production is intermittent. Not only is it intermittent, but you can see that it can fall very rapidly and it can rise very rapidly. And those falls and rises wind power usually are called wind ramps. A ramp is a way of getting up a slope, for example. And those very rapid falls and those very rapid rises are very difficult for the electricity system to deal with, because when the wind power is rapidly increasing, the system operator has to tell other electricity generators to turn off so that the total demand is not exceeded. And when the wind power is decreasing, the electricity system operator has to bring on other generators that can make up for the drop in the renewable power. And so I think you begin to see a couple of things from this. One is that when you have a significant amount of renewable energy on an electricity grid, then you need complementary generators. You need backup generators who can be turned on and can be turned off very rapidly. And the current technologies of generators that fall into that category are gas turbines. And we saw a little bit about gas turbine installation in the US yesterday, and hydropower, believe it or not. Some types of hydropower are also very easy or relatively easy to ramp up and ramp down. And the other thing you can appreciate from this graph here is that these intermittency issues become more important as the penetration level increases. See, in this case here, with wind power producing only about 6% of Alberta's electricity, these rapid decreases and these rapid rises in electricity production are not a big deal for Alberta to handle. But imagine if wind power was 60% of the electricity grid. How would you deal with these very rapid increases and decreases in power output? And there's a few countries around the world where that is important. The country that has the largest penetration of wind power is Denmark. And Denmark has over 50% of its generating capacity is with wind power. And later on in the course, we're going to look at how Denmark deals with the intermittency issue, because it deals with it in a way that is probably not what you would predict that it would do. Okay, if we go to the actual wind farm itself, then those intermittency curves, which was for the total wind power in Alberta, also occur at each individual wind farm. So here's some data that I got from a wind farm in southern Alberta. It's a 70 megawatt wind farm. It's a fairly old wind farm. So 70 megawatts is the maximum power that wind farm can produce. But like all other wind farms, it can also produce zero power if the wind's not blowing. And this data that you see here is 5-minute average power output from the wind farm. That's just the way the data came to me. I didn't do anything particularly in processing the data. That's just the way the wind farm owners gave it to me. And if you look at the 3 days here, and I've taken 3 days simply because it makes a neat sized graph, you can see that the maximum difference in those 5-minute data is approximately half the rated power of the wind farm. So the wind farm can drop from a power output of 70 megawatts to something around about 30 megawatts in 5 minutes. Okay, that's a pretty rapid decrease, particularly from the context of the people that are operating the electricity grid. Because as that drop is occurring, they've got to tell other electricity generators to turn on to make up the difference. So intermittency is extremely important. It's important for slightly different reasons with solar. Solar, part of the intermittency with solar is totally predictable because solar photovoltaics cannot produce at night. But during the daytime, the advent of clouds in the sky and things like that make similar sorts of variations in power output occurring for solar systems as well. Okay, so the summary of where we've got so far is that without labouring the point, there is a great need to reduce the amount of carbon dioxide that humans are pumping into the atmosphere. Another issue that I haven't really spent any time on, but I think it's intuitively obvious that energy usage and standards of living are related. And so we have a dual challenge in this world because a lot of people in this world do not have an adequate standard of living. If we're going to bring everyone in the world up to a decent standard of living, and we're going to keep reducing the amount of carbon dioxide that goes into the atmosphere, that's going to be very difficult. I've emphasised that renewable energy is cost competitive in many countries. As I said, for example, in Western Europe, it is now and has been for several years the cheapest way to generate electricity. The penetration levels of renewable energy are increasing. Again, I haven't given you any data on that, but the reference material that I posted on Google Classroom has that information. So we're getting more slowly, far too slowly, in my opinion, but we are getting more and more renewable energy in the world's electricity system. And the technical way of saying that is that the penetration levels are increasing. And I've given you some indication that the intermittency of renewable energy is a major issue when we look at how renewable energy integrates with an electricity grid. And we're going to be spending quite a lot of time in this course looking at issues of intermittency and how systems can deal with it. Okay, here's some other issues. One of the important issues in terms of greenhouse gas effects and global warming is what is called the energy intensity of the technology. And that is measured in a whole number of different ways. The most common way of measuring it is what's called the global warming potential. In other words, how much carbon dioxide do you produce in producing, say, 1 kilowatt hour of electricity? If you take a coal-fired power station, then around the world, typically that's 1 kilogram of carbon dioxide per kilowatt hour of electricity. So if you live in a jurisdiction where there's a lot of coal-fired power, then every 6 hours or so that you use your laptop computer, you've generated a kilogram of carbon dioxide. Gas-fired electricity is typically about half of that. It's about 500 grams per kilowatt. If we look at solar photovoltaics, then it's of the order of 3 grams. So here we're looking at the global warming potential of a number of different PV technologies. The numbers don't change drastically from technology to technology, but you can see that we're looking at around about 3 grams per kilowatt hour. So substantially less than the gas-fired global warming potential, and even much smaller than the coal-fired potential. I'll give you some data on wind power in just a moment after I finish the rest of the things on the slide. One of the interesting things that is happening in Canada, and I'm hopeful to learn more about what's happening in the northern parts of Russia. There are a lot of photovoltaic systems in Canada, in the north of Canada, but they have the obvious problem of how to produce power in wintertime. I have an association with what's called the Arctic Institute of North America, which does research into a whole lot of different issues of living in the Arctic. And they have a research station in northern Canada, up near the Arctic Circle, where they have installed a lot of photovoltaics, and they're trying to deal with the issue of how to produce renewably power during the wintertime. And I have a meeting in a week's time with the manager of the research station up in the Arctic, and we're going to talk about whether it makes sense to look at hydrogen production from renewable energy in summertime to store as fuel to use in wintertime. There are other environmental costs. For example, coal-fired power stations use a lot of water, and water is becoming one of the scarcest resources on this planet. Yet, as far as I know, there are virtually no coal-fired power stations that pay for the water in any way, shape, or form. There are issues like bird and bat deaths for wind turbines, which I'll mention very briefly. I've talked a little bit about embedded energy and carbon dioxide costs of renewable generators. I've given you this information down here, the solar photovoltaics, and I'll give you some information on wind turbines in a moment. And there's general issues of sustainability of renewable energy resource, of technologies, because even though they produce substantially less carbon dioxide per kilowatt hour than conventional power generators, there's still room for improving on them and get those numbers even lower. So here's typical numbers for wind turbines of different sizes. And there's a lot of research that people have done on what are called life cycle costs or life cycle impacts of these technologies. So we're looking on average somewhere around about 8 grams per kilowatt hour for wind. So again, substantially less than coal, substantially less than gas-fired generators, but again, there's room for improvement. Here's an example of where a very big improvement for wind turbines has to occur. The blades of wind turbines, we will see when we look at wind power in this course, are made from composite materials. They're basically fiberglass. And fiberglass is a mixture of petroleum resin and reinforcing material. And large wind turbine blades on the largest of the turbines that are being built at the moment, each of those blades weighs something like 50 tons. And 50 tons of solid petroleum and reinforcing is a real problem to get rid of at the end of the lifetime of the turbine. At the moment, there are very few things that can be done with old wind turbine blades. One of the things that can be done is to burn them, and that usually goes under the name of pyrolysis, which is burning without oxygen. Alternatively, they're dumped into landfill. And photographs like the ones that you see here are not good photographs for the wind energy, for the wind industry. There's a big move in the wind industry to make blades from sustainable materials. And those sustainable materials can include things like what are called bioresins, resins that are made from natural materials. Another way of dealing with that problem is to use what's called a thermoplastic resin. And a thermoplastic resin actually melts at a high temperature rather than sets at a high temperature, which is what happens with standard fiberglass. So a thermoplastic resin can be reused. So if you take an old wind turbine blade, in principle, you can melt it and make another blade. So that's one thing that people are looking at. I'm working with some colleagues at the University of Calgary in looking at using thermoplastics for wind turbine blades. And I also work with a group at a university in Brazil. And this university is on the edge of the Amazon rainforest. And the Amazon rainforest has a lot of biodiversity and a lot of natural materials that are good candidates to be reinforcing materials for wind turbine blades. So hopefully sometime in the not too distant future, this problem will not be as severe as it looks in this photograph here. If we move on to photovoltaics, there is also a problem here. The basic problem with photovoltaic modules, again, is a recycling problem. And a photovoltaic module has 60 or 72 mainly silicon-based solar cells. It has gold and copper connectors. It has an aluminium frame around the edge of the module, and it has glass on the front panel, on the front of the module to protect it from the sun, to protect it from the environment. The glass and the aluminium are easy to recycle, but the rest of it is difficult to recycle. And one of the difficulties in recycling photovoltaic modules is to develop a system by which you can collect modules from a lot of different places. Because we saw yesterday, a lot of photovoltaic systems are actually quite small. They're distributed energy generators. They're on people's houses, or they're on top of factories, or on the top of shopping centres. So just the physical process of collecting these modules and taking them to a recycling place can be a major issue. And this particular article, which is in the Harvard Business Review from June this year, talks particularly about the situation in North America and how it's predicted that by 2050, there'll be many millions of tons of solar photovoltaic materials that need to be recycled. And the article argues that we should be starting to develop the techniques or the procedure or the system to do that recycling now before we're hit by the large amount of modules that have finished their 20-year lifetime round about 2040, 2050, those sorts of time. Oh, no. Okay, the last thing that I wanted to talk about or introduce is something that I'm hoping to get a lot of feedback from people here. What is the current state of renewable energy in Russia, and what can you do, or what can you see are ways to increase the penetration levels of renewable energy in Russia? I've put these papers that I just did a Google Scholar search and downloaded a number of papers that looked interesting in their description of the Russian scene. If you have some spare time over the next few weeks, I would be very grateful if you could read some of those and give me your opinions on what's happening in Russia, and maybe we can talk about it towards the end of the course. So here's one paper that talks about the barriers and the mechanisms of developing wind energy in Russia. And another one here is a very interesting paper because I deliberately showed you part of the actual paper itself rather than the title and the abstract. And the reason I'm showing you this is that this covers material that we're going to be looking at in this course when we get on to wind power. So if you look at equation 1 here, it is a very well-known equation for the power output of a wind farm. So P is the power output in kilowatts. There's a power coefficient, as it is called, C subscript P. There's an efficiency, which often can account for the mechanical losses in the turbine drivetrain or the electronics losses in the power electronics. Capital A is what's called the swept area of the blades, the circle that the blades sweep out as they rotate around the turbine axis. U is the wind speed. And you will see here, if you look carefully at this formula, it is wind speed cubed, U to the power of 3, which is a very, very strong dependence of power output on wind speed. This equation actually explains a lot of the issues that are involved with wind power. And so when we get on to looking at wind power later on in this course, we're going to be spending quite a bit of time talking about equations that look a lot like that. If you go down here, you'll see in red a typical power curve for a wind turbine. So you can see wind speed in meters per second and the power output in kilowatts. And this is a 4 megawatt plus wind turbine. And you can see this region here between typically 5 meters per second and 10 meters per second, where the power output increases rapidly with wind speed. Basically, it's this dependence here. And if you read this article here, they say if you have an average wind speed of 5 meters per second, then you will get something like 375 kilowatts. Now, I'm going to tell you that's wrong. The authors of this paper have fallen into a very common trap of doing wind resource assessment based only on the power curve, as this red curve is called, of the wind turbine. You might like to think what could be the mistake in doing that. If you have an average wind speed of 5 meters per second, why don't you just simply go along to 5 meters per second on the power curve and look at how much power you get out? Okay. This is not a very fair question for you people at the moment because you probably haven't learned enough about wind turbine performance to analyze this. But the mistake that these authors make is that by the appropriate international standard, this power curve is determined by averaging the power and the wind speed over a 10-minute period. The procedure for determining the power output for a power curve for a wind turbine requires a field test, a test of the turbine in a real situation. And the data has to be collected in such a way that you make 10-minute averages of the wind speed, 10-minute averages of the power output, and you take the average of those curves and you get the power curve for the wind turbine. When you talk about an average wind speed, you're usually talking about a yearly average. Okay, when if I look at databases for wind energy that include Calgary, then the average wind speed for Calgary is about 4.5 meters per second. That is a long-term or yearly average. So what these authors have done is to use a long-term average wind speed with effectively a short-term average power curve. And that mismatch in the time period of the averaging makes the mistake that they've got there. An average wind speed of 5 meters per second will generate a lot more than an average of 375 kilowatts. And we'll look at ways using SAM where we can turn the turbine power curve into what's usually called the annual energy production. How many kilowatt hours per year does my wind turbine produce? So those, I don't expect you to grasp the key issues that I'm pointing out by showing you this paper, but I'm telling you that this is stuff that we're going to be doing quite a bit of when we get into the section on wind energy. Okay, I think this is the last slide of the presentation, and it's a very interesting one because it talks about what they call geophysical constraints on the reliability of solar and wind power. So they're going back to the issue of dealing with these renewable energy technologies that are essentially intermittent. How do you deal with it with a combination of wind and solar power and possibly storage or no storage? And what I found extremely interesting about this analysis is that you see, here's Russia. So my laser pointer is pointing out all the results from figures A, B, and C for Russia. And if you look over here, here's Canada. And the situation on a sort of macro level, a system level for Canada is actually very similar to the situation for Russia. So what this says, and I don't have time to go into a lot of detail about the way the results were determined, and I'm not sure that I really understand them anyway, is this is showing that with the color coding here, you can see that in terms of reliability, what percentage of the time will the electricity system be able to produce the power that is required. The color yellow means high reliability, and you can see that both Russia and Canada are in the high reliability region, much so than many other countries. But they're in the high reliability region by having a large percentage of their renewable energy coming from wind. And that's not particularly surprising because both Canada and Russia are high latitude countries. Now, we do have parts of Canada where the solar resource is extremely good, but over the whole country, the wind resource is much better. And so this analysis is suggesting that if Canada wants to have a renewable energy system with a high penetration of renewable energy, but also a reliable system, then it has to be mostly wind. And exactly the same story holds for Russia as well. I think that is, that is the end of my presentation for the introductory lecture. Don't go away just yet because I've got something else that I want to share with you. But I'll just pause for a moment and ask if anybody has any questions at this point. And feel free to put the questions in the chat if you have any. And also feel free, if questions come to you after this lecture has finished, you can always email me. I'm happy to receive emails from students with questions because it means that you're thinking about the material that you're being presented with. Okay, well, at the moment, there isn't any questions coming up, but please, if you do want to use the chat to do that, then do so. What I'm going to do now is to give you a little bit of homework. And the reason that I'm doing that is that starting next Tuesday, we're going to look at hydropower as the first of the renewable energy technologies that we're looking at. And when we look at hydropower, we're going to need to be able to analyze hydro turbine performance. So what I've given you here is a document that is called Cross-Flow Turbine Analysis. And I uploaded that document to Google Documents today, so it's available on the course site. And I recommend very strongly that you download this document and read it before the lecture next Tuesday. And in particular, what I would like you to do is tell me on Tuesday if there are things that you don't understand about the analysis that goes on in this document. Okay, so what we're looking at here is the typical way that we do basic performance analysis for fluid machines like hydro turbines. We're going to see starting next week that there's a huge range of different hydro turbine technologies. The particular one that I'm showing you here is called a cross-flow turbine. And a cross-flow turbine typically is used at the small scale. If, say, you have a remote village in Siberia and that village is near a river, then you could conceive of building a remote power system using a cross-flow hydro turbine to provide power for that village. And a cross-flow turbine looks in schematic form, as you can see here. So there is a water supply, and that water supply has a physical height above the center of the turbine. In scale terms, this height would typically be considerably larger than the diameter of the turbine, but I wanted to cut the image down enough so we could concentrate on the turbine itself. Okay, so that head H, and we can call that a net head, and I'll explain what we mean by net head when we get on to the course next week. That is the potential energy that is extracted by the turbine. So the turbine is connected to the water supply by a penstock, as it's called, that's the English name, which is just basically a term that describes the pipework or the tubing that connects it. The water comes down through the penstock. This would be a shut-off valve here to turn the turbine off if it's not needed, and it comes into a nozzle. Okay, so here is the inlet of the nozzle, here is the throat of the nozzle, and here is the nozzle itself. And the purpose of that nozzle is to direct the water onto the blades of the turbine runner. So runner is the hydro turbine name for the collection of blades. So here where you can see the axis of rotation of the runner, and so that runner rotates clockwise. The water comes down through the nozzle, goes through the blades in what's called the first stage, then comes out through the blades in what's called the second stage, and exits the turbine. Now, this is probably my favorite type of hydro turbine. And the reason that I like it is that it is very simple turbine to build. These blades are very simple in shape. They're often just circular arcs. Okay? They can be cut out of water pipe, for example. If you compare that to, say, a Francis turbine has very complicated blade design, and particularly when you're talking about small turbines, that can mean that a small Francis turbine is very expensive. So a cross-flow turbine is a good turbine to use, particularly when you're looking for small-scale systems, and for reasons that I'll talk about in subsequent lectures, when you have a fairly small head. Okay, so what I want to talk about now is the basic methods by which we analyze these turbines. How do we derive equations that give us the performance of the turbine? How do we decide how fast the blades have to rotate. Omega is the angular velocity of the blades. How do we design the nozzle so that we maximize the efficiency of the turbine? What you should do, if you're a good design engineer, is make extensive use of computational fluid dynamics. I had a PhD student a number of years ago who did a lot of computations of cross-flow turbine performance. And we found that if you are careful in setting up the computational fluid dynamics, you can get very accurate answers for the performance of the turbine. What I'm going to be talking about now is at a level below that, just the very basic way in which we can analyze the turbine. And the way we do that is to use our basic conservation principles. We look at conservation of mass, we look at conservation of angular momentum, and we look at conservation of energy. And what I'm going to show you is that with those three principles applied in a very simple way, we can actually define many of the features of this turbine, and we can also determine the operating conditions that give us the best performance of this turbine. So what we do is we start off with conservation of mass. So what we say is that if we have an inlet flow coming into the nozzle, and we assume that the flow is steady, so it doesn't change with time, then the amount of water that is passing the throat of the nozzle per second is constant. Not only that, is that what you see here in the dashed red line, and please ignore the green slider as it's called there. Just pretend the slider is not there. I couldn't find an image that didn't have the slider in it, so I had to use this one. So this dashed line here shows the boundary between the nozzle of the turbine and the rotating blades. And what we can say is that if we know how many kilograms per second of water is coming through the nozzle throat, if the flow is steady, then that's the same number of kilograms per second that's going into the blades. So the first principle that we use is conservation of mass. And if you follow through very simple arguments that I've got here, that defines the radial velocity going into the turbine. And we can do even more than that if we make the requirement that the radial velocity has to be uniform on entry to the blades, and you might like to think about the reasons why we would want that, we can actually determine the shape of the nozzle. Okay, so equation 3 is actually an equation for the height of the nozzle in terms of the angle from the throat. And if we move on from there, we can say what we need to do with the nozzle of this turbine is to convert all the available head into kinetic energy. If you know anything about Pelton turbines do exactly the same thing. The nozzle of a Pelton turbine converts all that available head of the Pelton turbine into kinetic energy, which then is impacted on the turbine runner. Cross-flow turbine does the same thing, which allows us to relate the head to the velocities. And I'm just about running out of time, so I'm going to skip through the rest of it. But if you follow through the pretty simple arguments that come down to equation 8, we've actually been able to design many of the features of this turbine, as well as determine the conditions in terms of the angular velocity of the blades that are going to give us maximum performance. Okay. So this idea with these very simple principles of conservation of mass, energy, and angular momentum We're going to use them several times through this course in order to look at how we can design or how we can fix the basic features of our turbines, wind turbines and hydro turbines, as well as determine the conditions that give us best possible power output from the turbines. That's going to be a major theme of the technology descriptions in this course. So I'll finish there because it is 10:30 your time. But I would very much like it if you could download this short document and read through it before next Tuesday. And if there's anything in it that you don't understand, please send me an email or ask me when we have the lecture on Tuesday. So with that, I shall stop sharing that and finish for today, unless there are any questions that people have. No, it doesn't look like it. But again, as I've said several times, feel free to email me or bring questions to next class. Because if you understand the way that analysis is done on the cross-flow turbine, then you will understand all the turbine analyses we're going to do in this course. Okay, I shall finish there. And no questions and nothing in the chat. So I think we're finished for the day. Thank you, everyone, for listening and staying to the end. That's very impressive. Thank you.
Thank you.
See you then.
Bye-bye.
Bye.
Bye-bye.